Question 41 asks, which of the following diatomic molecules is predicted by MO theory to be diamagnetic? So diamagnetic means it has all electrons paired up with another electron with opposite spin. One thing that we can actually realize is that anytime a compound has an odd number of electrons, it must have at least one electron that does not have a partner, meaning it's an unpaired spin, meaning all compounds with odd numbers of electrons are paramagnetic. So what we can do actually is check a couple of our possibilities right away as being paramagnetic, which we can rule out. So what we're going to do is go through our list of A to E and calculate the number of valence electrons in each of these molecules. Oxygen is 2 times 6, which is 12. O2 plus is 1 less than that, which is 11. C2 is 2 times 4 is 8. C2 plus is 1 less than that, which is 7. B2 is 2 times 3 is 6. So what we can do here is rule out B and D as being diamagnetic because we know they're paramagnetic because they have an odd number of electrons. So we're down to O2, C2, and B2 as possibly being diamagnetic. So what we'll need here is our MO diagram. We have one that we can use for boron and carbon, which will look sort of like this. And then we have our pi's. And those come from our p orbitals. This is the one we use for boron, carbon, and nitrogen. And so we can use this one for boron and carbon. We'll do boron first. We need 6 valence electrons to add in here. We go 1, 2, 3, 4, 5, 6. Boron has 2 electrons in the pi orbitals. That's the 1 pi u. 2 electrons in there that are not paired up. So this one is definitely paramagnetic. Carbon 2, which is option C, has 2 more electrons than boron, and I'm going to change the color here to red so we can tell them apart. Adding 2 more electrons pairs those unpaired electrons, and so for C2, all electrons have a partner, and therefore that compound is going to be diamagnetic. We can do the last one, which is oxygen, which is A, and it has a slightly different MO diagram. Which has the 3 sigma G lower in energy than the 1 pi U. And then these ones are the P's. Not the neatest writing in the world, but that's okay. We got 12 for oxygen. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you can see for oxygen, there are 2 electrons that are not paired. Therefore, that one's going to be para as well. So the only one of these that's diamagnetic is carbon, which is C. Some true-false questions. 42 says, which of the following is true? A pi bond is the same strength as a sigma bond is false. Sigma bonds are stronger. And that's because end-to-end overlap of bonds leads to better overlap, more effective overlap, which leads to a stronger bond. Carbon-carbon double bond B consists of 2 pi bonds. That's false. A double bond between 2 carbons is a sigma and a pi. C, 2 separate py atomic orbitals interact to form a sigma and sigma star. No, that would be a pz. 2 pz's can interact form sigmas, the py's and the px's form pi's. D, a pi bond is due to side-to-side overlap of atomic orbitals. That is correct. If you have two orbitals that are oriented parallel to each other and you bring them close together, that will make pi bonds. So this one is true. E, a pi bond can hold 4 electrons, 2 above and 2 below the bond axis. That's false. All bonds, sigma or pi, can only hold 2 electrons, and so not 4, 2. The correct answer here is D. 43, which of the following statements is true? Intermolecular forces hold the atoms in molecules together. That's false. What holds the atoms together in a molecule is a covalent bond. B, the larger the molecule, the lower the viscosity of its liquid phase. That's generally not true. The larger a molecule, typically the stronger its dispersion forces, and the stronger its dispersion forces, typically the higher its overall intermolecular forces strength, and that would make it more viscous, not less viscous. C, pH 3 is a higher boiling point than NH3, so that would be suggesting that pH 3 has stronger intermolecular forces. That's actually not true. NH3 has stronger intermolecular forces because it has hydrogen bonding. D, hydrogen bonding is a very strong form of dispersion forces, not dispersion, dipole-dipole. E, surface tension is a measure of the energy needed to increase the surface area of a liquid. That is true. That's one way we could define surface tension for sure. Question 44 says, which of the following molecules contains a double bond? And to get this, what you would need to do is draw out the Lewis structures for each of these compounds and see which one has a double bond. So we can go through these. A is N2. We start out by drawing the skeletal structure with the atoms connected by single bonds, and we add up the number of valence electrons for nitrogen. So 2 nitrogens is 2 times 5 equals 10 valence electrons. We've already used 2 to make the single bond between the 2 nitrogens, leaving behind 8, and we use those electrons to fill up the outer octets. So we can go 2, 4, 6, 8, and now we're out of electrons. Now we check to make sure everything has a full octet, and if it does not, make multiple bonds. So the one on the right, this nitrogen on the right, is actually okay, but the one on the left only has 4 valence electrons. So it needs 2 more, and the way we give it 2 more is by forming multiple bonds by bringing electron pairs down from the neighboring atom to make multiple bonds. So we can take 1 down from here, 1 down from here, and we end up with nitrogen with 3 bonds and 2 lone pairs, 1 on each nitrogen. That is a triple bond, which is not a double bond. So A doesn't work. B, we have PCl, Cl, 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 Cl. Phosphorus has 5 valence electrons, and chlorine has 7. And that is a total of 40. We've already added in 5 single bonds, which is 10 electrons. We subtract that from our total, which leaves 30. We use the 30 to fill up the outer octets, so we can go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. We're all out. Every atom now has at least a full octet. The phosphorus in the middle has 10 valence electrons, which is exceeding the octet, which is all right because phosphorus is in the 3rd row. If you're in the 3rd row or below, you can go above an octet. Everything here has formal charges of 0, so we're done our structure, and as you can probably see, there are no double bonds anywhere to be seen. Keep going. We have CH2O, COH, H, H. This is formaldehyde. You might have seen this one before. We add up our valence electrons. We have 6 for the oxygen, 4 for the carbon, and 2, 1 for each hydrogen. It's 12. Minus 6 for the 3 bonds we made leaves 6. We fill up the outer octets. Hydrogen already has full. That can only take 2 electrons, so it's both hydrogens are happy. The oxygen can take 6 electrons, 2, 4, 6, which uses up all of our electrons. Next, we check to make sure that all atoms have a full octet, and the outer atoms do, but the central carbon does not. It only has 6 valence electrons. So what we need to do for it is bring a pair of electrons down off the oxygen and make a multiple bond. And so our actual structure, I'll draw it on the right, should look like this. And there are 2 lone pairs left on the oxygen. And we have our structure complete. That actually has a double bond, so that is the correct answer to the question, which is C. We can do the next 2 compounds too, though, just to say that we did them. We have C2H2 and I2. D, C2H2 has a structure which has the carbons in the middle and the hydrogens on the outside. Symmetric. Carbon has 4 valence electrons, so we have 2 times 4 plus 2 times 1 is 10 electrons, minus 6 for the bonds that we made, leaves 4, and we have 4 electrons now to place. The outer atoms, which are the hydrogens, are already filled, so any remaining electrons, once the outer atoms are filled, goes on the central atoms. So we have 4 electrons to place on these 2 carbons. We can either put both pairs on 1 carbon or 1 pair on each carbon. In this case, you end up with the same result. So I'm just going to put 1 pair on each carbon. If you look at these structures, what you can see is that the central carbons do not have full octets. They only have 6 electrons each around them. So what we can do is take 1 pair down to make a multiple bond, which would give us something that looks like this. Hydrogen, carbon. We've used the pair on the left carbon to make a multiple bond. That satisfies the octet of the carbon on the right, because it now has 8 electrons, 4 in the double bond, 2 in the single bond, and 2 in the lone pair. But the carbon on the left does not have a full octet, so we're going to have to take the second electron pair down as well. And that gives us hydrogen, carbon, carbon, hydrogen. That has a triple bond, so clearly that isn't the answer to the question. Of course, we know that anyway, because we already got the right answer. The last one is I2. And so I2, not hydrogen, I2 has just a single bond between them to begin with. We add up our valence electrons, which is 7 plus 7 is 14. Minus 2 for the bond we just made is 12. Fill up the outer octets. We have 2, 4, 6, 8, 10, 12. That exhausts all of our electrons. We have nothing more to place. Both atoms here have full octets, and all atoms here also have formal charges of 0. So that is our final correct structure. Clearly no double bond in that one either, as we sort of already knew. Question 45 is looking for the best Lewis structure for ClCN. So the structure of this actually is just the way it's drawn. Carbon is the least electronegative. It's in the center. It has a nitrogen on one side and a Cl on the other side. We add up our valence electrons. We have 7 for the chlorine plus 4 for the carbon plus 5 for the nitrogen is 16. Minus 4 electrons for the 2 bonds is 12. And we use those 12 electrons to fill up the outer octets first. 2, 4, 6, 8, 10, 12. We've used all our electrons, and now we're down to 0, left to place. Our structure has filled the octets of the outer atoms, but the central carbon only has 4 valence electrons, and it wants an octet. It wants 8. So we're going to be having to make multiple bonds to that carbon as well. In this case, though, we have a number of choices. We can either take 2 electron pairs off the chlorine, or we could take 2 electron pairs off the nitrogen, or we could take 1 pair off of each. That would lead us to 3 possible structures. The first would look like this, where the nitrogen hasn't given anything up, but the chlorine has given up 2 pairs to make a triple bond. We'll call this structure A. Or we take 1 off each, Cl, C, N. Each now has 2 pairs of electrons. We'll call that B. Or we take both off the nitrogen, and we have Cl, C, N with a triple bond, 1 pair on the nitrogen, and all the pairs left on the chlorine. So how do we decide which of these 3 structures is best? What we have to do is look at formal charges, and we're going to be using formal charges here to determine which is the best, A, B, or C. So we'll start with compound A. The chlorine has 7 valence electrons, and we subtract from that the number of bonds, which is 3, the number of unshared electrons, which is 2, and 7 minus 3 minus 2 is plus 2, which is kind of an ugly formal charge to have on an atom. Typically, formal charges are +1 or -1. Very rarely will you ever see magnitudes greater than 1 for formal charges. The carbon has 4 valence electrons, minus 4 bonds is 0, so the carbon at least is happy in this structure. The nitrogen has 5 valence electrons, minus 1 bond, minus 6 unshared electrons, which gives us -2. So almost without even looking at the other structures, we can say that this one is probably going to be wrong because it has very high magnitude formal charges. Compound B, the chlorine here has 7 valence electrons, minus 2 bonds, minus 4 unshared electrons is +1. So we put a plus there. The carbon is 4 minus 4 bonds is 0. The nitrogen is 5 minus 2 bonds minus 4 unshared electrons is -1. So now we have formal charges of +1 and -1, which is better than the previous one, but still not ideal, especially since the positive charge is on a fairly electronegative atom, which is chlorine. Last, we have structure C. Structure C, the chlorine has 7 valence electrons. We subtract 1 for the bond. We subtract 6 for the 3 pairs of electrons that are not shared. That equals 0. Great. Carbon is 4 valence electrons minus 4 bonds is also 0. And the nitrogen is 5 minus 3 bonds minus 2 unshared electrons is also 0. So this structure on the right is great because it has no formal charges on any atoms that aren't 0. So this one is going to be our best structure. (46) says, for the nitrate ion, which of the following statements is false? Well, let's begin by drawing the structure of the nitrate ion. We have nitrogen, we have oxygen, oxygen, and oxygen. Our valence electrons here is going to be 5 for the nitrogen, plus 3 times 6 for the oxygens, plus 1 because it has a negative charge. Every negative charge adds an electron, every positive charge removes an electron. So that equals 24, I believe. And we've added 3 bonds, which is 6 electrons, which leaves us with 18 electrons. And we use these to fill up the outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used all our electrons and we're down to 0. And there's none left to place on the central atom. Do all the atoms have full octets? That's our next check. The outer oxygens all do, but the central nitrogen does not. It only has 6 valence electrons, so we want to fill its octet, and to do so, we're going to be making multiple bonds between the nitrogen and neighboring oxygen atoms. So here we have a choice. We have 3 oxygens, and they're otherwise equivalent. We can use any one of those oxygens to make the multiple bond. So if we use the left-hand oxygen to make the multiple bond, which would bring the electrons down to like there, we would get 0, 0. Oxygen, double bond, nitrogen. The other oxygens remain the same. And that oxygen now has 2 left. If instead we used the top oxygen to make the multiple bond, we would get a structure that looks like this. Oxygen, oxygen. Finally, we can use the right-hand oxygen, and we get a structure that looks like so. So we have 3 different structures. To finish these structures off, what we need to do is work out our formal charges. The nitrogen in the center of all 3 of these is the same. The nitrogen has 5 electrons, and it has 4 bonds, equals +1. So all the central nitrogens here have a positive charge in the middle. The oxygens that are doubly bonded have 6 valence electrons minus 2 bonds minus 4 unshared electrons is 0. So all the double bonded oxygens have formal charges of 0. The singly bonded oxygens have 6 minus 1 minus 6 equals -1, charges of -1. So we're going to put a negative charge on all of those oxygens like you see here. So we have these 3 structures. They are all basically equivalent, except we use different oxygens to make the multiple bonds. We would call these 3 structures resonance structures. And we connect them with these double-headed arrows. Don't confuse a resonance arrow with an equilibrium arrow. They both point in 2 directions, but they do mean different things. All right, maybe we can now answer the question. 46A says it has 3 resonance structures. Absolutely does. We just drew them. The N is sp2 hybridized. So our N in the center, we would call that atom an AX3 atom. It has 3 electron groups. 3 electron groups means that it's sp2 hybridized. So yes, indeed it is. It contains 3 sigma and 1 pi bond. So the double bond is a sigma plus a pi. These ones are sigmas, these ones are sigmas. So if you count those up, we do get 3 sigmas and 1 pi bond. The formal charge on the nitrogen is +1. I think we've established that. Real bond angles deviate from ideal. So this happens when you have a double bond or a lone pair that pushes the other bonding electron groups away from it. In this case, it kind of looks like that might be the case because each of these structures has a double and 2 singles. But keep in mind that when we talk about these as resonance structures, what we mean is that the real true structure of this molecule is not any one of these structures or any one of these structures interconverting between the others. It's actually a blend, a mixture of all 3. The real structure, we would say, would look something like this. Can't draw it properly by following the rules of Lewis structures. Got a positive charge in the center, and each of the oxygens will have a charge of -2/3. So in that sense, all 3 of these bonds are identical to each other. No one of those bonds is going to push the other 2 bonds apart. So the real bond angles in this molecule will be exactly the same as the ideal bond angles, which are 120 degrees. So E is the one that is false. Draw all resonance structures for the carbonate ion. So we have carbon, oxygen, oxygen, oxygen. We add up our electrons. We have 4 from the carbon plus 3 times 6 for the oxygens plus 2 for the charges, which gives us 24. We've drawn 3 bonds already, which is 6 electrons, which leaves us 18. Fill up the outer octets. 2, 4, 6, 8, 10, 12, 14, 16, 18. And now we check to see if everything has a full octet. The outer atoms all do, but the central carbon does not. It needs 2 more electrons, and we're in the same situation as we were in the last question, where we need to form a multiple bond between the central atom and one of the outer atoms, and all the outer atoms are equivalent. So we can either use the left-hand carbon, the top carbon, or the right-hand carbon. If we use the left-hand carbon first, maybe we'll draw this in red, we'll get a carbon, double bond oxygen, single bond to this oxygen, and a single bond to that oxygen. If instead we used the top, we're going to bring that one down. We get carbon, double bond with this oxygen. Or we use the right hand and we get carbon, oxygen, no. Go back there, single, single, double here. Now we have to put in all of our formal charges. The oxygens with a single bond will have formal charges of -1. Which will look like this. We need our resonance arrows to show that these are resonance structures. And that looks like that. That's it. We've got 3 resonance structures for that. 48 says, the following is the Lewis structure for glycine, an amino acid, under physiological conditions with formal charges not shown. Which atom has a formal charge of 1? Well, let's start at the top. Atom 1 is the nitrogen. As you can see, it's making 4 bonds and has no lone pairs. So its formal charge is going to be 5, which is its valence electrons, -4 for the number of bonds, -0 for the unshared electrons, equals +1. We landed on the correct one already. Let's put that in. We can finish the other ones off anyway. Carbon is 4 valence electrons -4 bonds on carbon 2, -0 is 0. Atom 3 is oxygen, and it has 6 valence electrons. It's making 2 bonds, and it has 4 unshared electrons, which gives it 0. And the last one is 5. Did I skip one? Yes, 4 is a carbon. Carbon is 4 valence electrons. This is making 4 bonds, 2 singles and a double. No unshared electrons, gives it a formal charge of 0. 5, we have oxygen. It has 6 valence electrons. It's making 1 bond. It has 6 unshared electrons around it, which is -1. So we can give it a -1 charge on the structure. So the correct answer we kind of landed on right away is A. Question 9, what's the molecular shape of NH2Cl as predicted by the Vesper theory? So to do this one, we need to correctly draw the Lewis structure first. So we can go nitrogen in the center because it's the least electronegative, except for hydrogen. Like hydrogen is never the central atom. I mean, nitrogen's more electronegative than it anyway, but Cl. Add up our electrons. We have 2 times 1 for the hydrogens, plus 5 for the nitrogen, plus 7. And that gives us a total of 14. Minus 6 for the 3 bonds that we drew is 8. We use those 8 electrons to fill up the outer octets first. The hydrogens are already satisfied, so we're going to put 6 around the chlorine to give it 8 electrons. We've added 6. We have 2 left over. Leftover electrons goes on the central atom. Those go on the nitrogen, down to 0. So we're done with our structure for now. We can check our formal charges. You can double check this, but all of the atoms here will have formal charges of 0. All atoms have their outer shells filled. They have noble gas configurations, so everything is happy here, and this is our correct final structure. We would classify this compound as an AX3E compound. It has 4 electron groups, which are 3 bonds, 3 single bonds, plus a lone pair on the nitrogen. And the shape of a compound like this, an AX3E, the electron group geometry would be tetrahedral, but the molecular geometry would be trigonal, pyramidal. And on to question 50. According to VSEPR theory, a molecule with the general formula AX3E2 will have a blank molecular shape. AX3E2 means 5 electron groups. Something like this would have an electron group geometry of trigonal by pyramidal. It's the shape that looks sort of like this, where you have A in the center, and then you have something that goes up and down, the axial, and then we have the equatorial positions like that. 3 of these would be X's, and 2 of them you could think of as being like lone pairs, and something like that has a shape that we call T-shaped.